grainy.
Hello? Hey, I'm going to make an announcement. So, hey guys, Alpha Kappa Psi is holding a Tech Talk event with speakers from Google, Tesla, Intel, Kiwi, if any of you guys are into that. And other companies where they'll be talking about the different unique ideas that they're implementing right now that you'll see in the near future. There'll be free gongcha, cheese board, plenty more food, a raffle for some hot tech commodities, as well as a resume drop. If you're interested in how you can learn more about the future of technology and even more so, and how you can contribute, I'd highly recommend coming out today, Thursday evening at Anderson Auditorium from 7 to 9:30 over there at Haas School of Business. You can learn more at tinyurl.com/UCBhello. And that's all. Thank you all. Enjoy the lecture.
Okay. And with that, good morning. So, as Gireeja said, you heard the music from one of your classmates. So if you want to hear more music, send us some of your own and to E16A staff, and we'll just play it. Please make sure it's not copyrighted, though. Okay, so today we're going to move on with negative feedback circuits. So what we did last time is we looked at kind of ways to tame the op-amp and tie the feedback loop around it and make sure that the properties of the system are then determined by the properties of that feedback loop rather than the op-amp itself. And it was a great benefit because we could reuse the same op-amp with highly variable characteristics in various situations and change its nature just by tying appropriate feedback loop around it. And that allows us to use the same part in many different places for different functions, which is really nice. So we can manufacture these parts in large quantities and then reuse them however we want. So we're going to talk some more today how to easily spot the negative feedback, because if you remember last class we derived these golden rules, and one of them was very important and tied to the fact that there is actually negative feedback in the circuit. And so whenever you see an op-amp based circuit from now on, the first thing you're going to do is go check whether it's in negative feedback. If it's in negative feedback, then you can apply these rules and make your life significantly simpler in analyzing that circuit. Without that, you'll really have to kind of do a lot of the grunt work to really see what's going on. So we're going to do that first. And then we're going to look at one of the cool applications. A lot of people today are talking about machine learning and neural networks and things like that. So we can show you can actually, and they're actually looking to build very efficient hardware with it. So I'm going to show you some examples of that. And then hopefully from there we can go and look at how we can compose bigger blocks together to make even bigger functions. Right. So let's say the first thing is we want to look at the polarity of negative feedback. Meaning you're given a circuit, you want to wire it up. How do you wire up an op-amp in a circuit so you ensure it's in negative feedback and behaves well, right? So the first thing you're going to do is turn off independent sources. So this sounds familiar. It's like in almost every procedure of analysis that we do, we kind of turn off the independent sources. Thevenin, etc. Okay. Number 2, we're going to apply a disturbance at the output and then follow the loop, the feedback, to see it suppressed at the output. Right. So we're going to apply a disturbance, follow the loop all the way back to the output and see that that disturbance is suppressed. If that's what's happening, then the loop is in negative feedback. So let's do an example. So this is a source. So this is going to be our example. This is what's called an inverting amplifier. We're going to derive that later. One of the things just to note here, I kind of introduced this when we talked about the DAC, and then later I explained this was a signal source. Whenever you see a squiggly like this really means a signal. It's coming from some other circuit. It's just that when we analyze the circuits, we want to analyze piece by piece or block by block. So this is not really a power supply, a supply. It's just a signal source. It's representing a Thevenin equivalent of some previous circuit, right? And therefore, you should never use that as a supply of your circuit, right? That source simply does not have enough power to drive, let's say, this big amplifier through the VDD and VSS. So when we do this signal analysis, as you see, I don't draw VDD and VSS anymore, right? Because I'm only interested in how the signal propagates through the circuit, not in how the circuit is supplied with power. So when you're doing design problems, never tie the signal source to a supply pin of the op-amp. It's not going to do anything. Because, in orders of magnitude, these sources are like microvolts, millivolts. Op-amps need volts. Right, so there's like 3 to 4 to 6 orders of magnitude difference in the voltage that we're talking about here. So this is never a supply. Right? Just keep that in mind. We see a ton of problems on midterms and exams where people miss that and just tie the output of even the output of the op-amp as the supply of the next op-amp and things like that. Those things are never done. There's a separate set of batteries that supplies, like in your breadboards when you do it in the lab. You use separate sources to power up all the op-amps, and then the signal propagates from one input to another output, etc. Right? Okay, so let's check for negative feedback. Okay, so step 1, we null the source. Right, so that becomes ground. We have R1. We have a minus and a plus here. Okay, and so now here, this is my output. Now I'm going to do step 2. Make a change at the output. When I say make a change, what does that mean? Pretend I had some voltage source that I attached and I kind of moved that voltage up, right? And I want to see how the rest of the circuit behaves. So there is a disturbance here. Well, if this voltage goes up, what happens with this voltage over here? When I say voltage, I mean with reference to ground. Or we can say what happens if I move this potential up. what happens to this potential here at U minus? Increase. Why? It's correct, but let's think about why. Yes. Okay, but why? Okay, so some drop through the resistor. What is the current into the op-amp at this node, negative node? 0, right? So if the current is 0, can I just forget that the op-amp exists? Right? I'm just trying to figure out changing this node, what does it do to this node? If there's no current into the op-amp, I don't care that the op-amp exists. Okay? So what does this circuit remind you of? Voltage divider, right? Okay. So in a voltage divider, it's, as you said, like if you move the top potential, the bottom one is a fraction of that potential, so definitely it will also move up, right? It will move up by a smaller proportion, but still will move up, right? Does that make sense for everyone? If something doesn't draw current, it's not affecting the rest of the circuit, right? The op-amp doesn't draw the current from this node, so it doesn't affect this voltage divider circuit, right? It's kind of like in the touch. When we attach an open circuit to measure voltage, we don't really affect the voltage divider itself, right, in resistive touch. So it's the same thing here. Okay, well, now that I know my U minus is increasing, but it's on the negative terminal, how does the voltage change at the output of the op-amp? Remember the model for inside here, we had a voltage-controlled voltage source that was U plus minus U minus. Right? That was inside. So if U minus increases, what happens with this voltage? Goes down. Right? So U minus increases, this overall thing goes down. Okay, well, that's great news. So I'm just going to write it out for you here. Now the source. And then here, apply disturbance. Right. Okay, so this means it's in negative feedback. And I can draw my smiley face. Now I can move to the next step. This being in negative feedback means that I can apply golden rule number 2, which means that U minus equals U plus. And that's going to make my life very easy. Okay? So now let's try solve it. Okay. So we have negative feedback. That means golden rule number 2 applies. Right? And that was that U plus equals U minus. So now we're going to just draw it out and do the 7-step, like a shorter version of 7-step procedure, just so you can see that the basic circuit analysis applies to these op-amps. They're nothing special. They're nothing special. Really, it's just a controlled source. In fact, you don't even need that because of the golden rules. So let's take a look at that. So V in, I have R1, and that goes into the negative. If you're drawing, leave a little bit of space so we can mark all the labels. And so let's just go out and write out the procedure. The first thing we do, we obviously map the reference node. So we've already done that. These are our the grounds, so that is really our reference node. So we already did that, right? Then next thing is we're going to go and label the potentials, right? So I'm going to say, okay, U1 is here, U3 is here, and let's say U2 is here. And from here, we need to label the currents according to the passive sign convention. That's important. So, or actually, let's label the currents arbitrarily and we'll label the voltages. So, okay, let's do I1 is here. And let's say I2 is like this. There is also, I'll just label it here, I minus. Okay, it's not. But we know that that one is 0. But I'll label it just in case for people who are confused. Okay, so now that we have currents arbitrarily labeled, now we apply the voltages to elements according to the passive sign convention, right? So plus minus here will be VR1, and then plus minus here will be VR2. Notice I didn't really do that for the voltage source. Hopefully by now it's easy to read out what U1 is, right? So let's do that first. So what is U1? Just from this source. Vin, right? Okay. If you are confused about that, label the current on that, label the voltage and then of the element, and then just apply the definition. Similarly, for U2, what is that? What is U2? V out. Okay? And then, okay, this one might be tricky. What is U3? Yes. Okay, I think you're going in the right direction. That will help us solve things, but actually there is a simpler explanation. It's equal to a constant. You just need to figure out which one. Equals to 0. Okay, so can anyone explain why it equals to 0? Okay, so you're saying like because current is 0, then the U3 is 0. Well, if current is 0, then you could think what your colleague thought that, okay, now I just apply some sort of a voltage divider or something to figure it out. But yes? Yes, exactly. So this is the answer. So let me just write it down for everyone. Okay, say circuit in negative feedback. From there, GR2 applies. Yes, which means that U plus equals to U minus. We also know that U plus equals to 0. We just read it, right? That's just a property of this circuit, right? This is U plus. So U plus equals to 0. Therefore, from golden rule 2, U minus equals to 0. Right? We also know that U minus equals to U3. Right? Okay, because of that, U3 equals to 0. Does that make sense? This is very important. Okay? And what's even more important is don't get used to the fact that in a lot of op-amp circuits, it is indeed true that this node here will become a 0, but that's simply because the other node is at ground. Right? In many circuits, that will be the case. That doesn't mean automatically that U minus is equal to 0, always. No. U minus is always equal to U plus. If U plus is something else, well, U minus is that. Right? So in this circuit, just so happened that we put U plus to ground, and therefore, by ground rule, golden rule 2, U plus equals, or U minus equals the same thing, right? But that's not always the case, right? So always follow the golden rule. Don't assume. Some people call this virtual ground or something like that. Forget that name. That's a bad name, okay? Don't use it because it's confusing, okay? All you need to know is that when golden rule applies, U plus equals to U minus. And you'll be able to solve it always. Okay, make sense? Okay, so this makes our life a lot easier, as you'll see later. So let's then do the voltage equations. So we have VR1 equals I1R1. We have VR2 equals I2R2. Right? And these are just element definitions, right, from Ohm's law. And then we also have, for VR1, we have the voltage definition. VR1 is U1 minus U3. And VR2, as defined by plus and minus, is U2 minus U3. Well, from the top, we just know that U3 equals to 0. Right? So this is same as U1. This is the same as U2. And then this is V in. And this one over here is V out. I'm just substituting here. Okay? And we have another one, and this is KCL, that I1 plus I2 equals I minus. Do people see that one? So I'm doing KCL on the U3 node. So I1 goes in, I2 goes in, I minus goes out. And I minus is 0 because of golden rule number 1. Okay? So, from the top, we have that V in equals I1 R1. And we also have that V out equals I2 R2. Now we can just plug them into the KCL. So we have that V in over R1, which is I1, plus V out over R2, which is I2, equals 0. And that's our solution. So we just need to reorder it a little bit. From here, V out equals minus R2 over R1 times V in. And then when you say I need a voltage gain of this whole thing, that's a ratio of V out to V in. So that's minus R2 over R1. So what happens here is that the input signal gets multiplied by the ratio of the two resistors in the feedback, and there's a negative sign. So that's why it's called inverting amplifier. Now, depending on the ratio of R2 and R1, the amplification can both be greater than 1 and less than 1, right? Depending how you pick the ratio. So keep that in mind. It may become handy as a signal processing block so that you know this is an operation that happens on the input signal if you apply this circuit as a block, right? Okay, so does this seem tedious? A bit, huh? Okay, so let me show you a faster way. And, hopefully with a little bit of practice, you will be able to do that more easily. Now, I suggest at the beginning, go write out these equations. There are not that many to solve it. Typically, you won't have more than this. You only have less. But I suggest also trying the faster way, because it hopefully will cut the time and give you more intuition. But if you're in doubt, always come back and check with this. This is a very simple procedure, just a little bit of writing. Right. Okay. So we know that golden rule 2 says U plus equals U minus. We have that U3 equals U minus, right? And we have that U plus equals 0. So we... Oh, okay, sorry. So we know that U3 equals to 0. That's the critical thing to figure out what is the node on that circuit. Actually, let me just use it here so that you can see what I'm doing and the circuit. Okay? So the faster way only focuses on the KCL. Just like we did the faster nodal, well, I call it a magic kind of approach. And that's it. And then we automatically translate all the voltages into currents. So here it goes. I'm going to apply golden rule 1 and KCL together. Okay? So doing a KCL on node 3. I'm going to do it so that I'm looking at all the currents going out of the node. So the first one is going to be U3 minus U1 over R1. Okay? That's the current that goes, let me label it maybe with a different color. That's this current, right? U3 minus U1 over R1. That's this current. Then I'm going to write the current that goes that way, which is U3 minus U2 over R2. Okay? And then I'm going to write this current equals 0. And now I'm going to just substitute the values right there. U3 equals 0. That's because of the golden rule. U1 is V in. U2 is V out. I minus is 0. Does all this make sense? And there's my solution immediately. So let's see. What's left is minus V in over R1 minus V out over R2 equals 0. And from here, V out equals minus R2 over R1 V in. All right, so it's one equation. Yes? Oh, great question. Why did I choose to start from U3? It's just consistency, right? You could do it the other way around and then let me look at all the currents that go into the node. I like doing it this way because I can easily check my equation. All the terms in my equation should start with the node that I'm looking in. So U3, and then whatever the current is the other current. And I'm doing it that way, all the currents are going out of the node. So it's just something simple to remember. And yeah, last time we did it for nodal for just an arbitrary circuit, we did it exactly like that as well. So just because when you have more than one node, it becomes messy and you want to make sure that you can keep track of what you're doing. But yeah, great question. Does it make sense? Yes? Great question. Is the power source turned off? Meaning the signal source. It actually doesn't matter. And the reason is that the only thing that defines this red current is the potential difference between these two nodes, U3 and U1. And then I actually went and here I replaced U1 with V in, right? So I used the fact that, hey, U1 is actually V in. Right? So instead of writing I wrote that here as a separate kind of equation. And when you're writing a lot of these equations, it's boring, right? So then I just acknowledged that by doing this in-place substitution here, right? So again, there's a lot of steps here. That's why we kind of went through it one at a time. But hopefully in time you can just go like, Jedi Knight and just write this equation, right? And with a few weeks of practice, you'll be able to do it. But it will save you time on an exam when you're trying to do quick analysis. But you have to practice it to be good at it. And a good thing, for example, is being consistent about the nodes and things like that. If you try it and it's not coming out, always come back and check with these. It's a more tedious approach, more equations to write, but it's basically the same thing. Okay? Make sense? Yes?
So in the last lecture, we talked about the golden rules, I plus equal to I minus equal to 0. So in that case, is it easier to do them separately?
Actually, the golden rule should be I plus equals I minus equals 0, not plus. Because each of the currents is separately 0. It goes into an open circuit, right?
So should we do it separately or add them up together?
So here is where I applied golden rule number 1, right? I minus equals 0. Or basically here, right? Yeah. So you will always use both of them, golden rule number 1 and number 2 in your circuits, right? In order to solve it. Okay. Any other questions? This is clear? Okay, good. So let's do another example. Okay. This one we're going to call Transresistance Amplifier. Okay. It's useful to know these names because that's just a function of the block. Later, you see when we derive it, you never need to go back and rederive this stuff. You just know it. It's your library function. You can call it and it does that. Right? So this one, there is actually a signal. Again, this is a signal source. It's not like a current supply. And does something like this. Okay. So why don't you take a minute and tell me if this circuit is in positive or is in negative feedback or not? See if you can apply the two-step procedure and see how the loop behaves. Okay, any ideas? Negative feedback or not? No? Yes or no? No? Okay. Okay. So let me draw it, and then let me see if someone can walk me through it. So we null the source. All that's left is just a resistor around. Right? Okay. Okay. So anyone wants to walk me through it? No one? Okay. So you want to do a disturbance at the output. Okay.
Then that disturbance will increase the voltage at the plus terminal, correct?
Okay. Why is that? Intuitively, it's true. What's the current through this R? 0, right? So the current through this R is 0. What's the voltage at V plus? It's the same as that one at the output. So if the output has moved, this has moved, and actually by the same amount. Right? Good. So plus is moved. Now? Yes. Further increases, and by a lot. Right? Okay. So this is definitely not an NFB. Right? And of course, it's not really good. Okay? So let's see how we can fix that. Any ideas? You came to the lab and you kind of wired up the circuit and it just like shot into one of the supplies and you're like, what the heck's going on? Yes? Okay, so we flip the polarity, right? Good. Okay, let's try that. And that's as easy as that in the lab. It doesn't work, you just flip the polarity. And all of a sudden it starts working. Okay, so let's do that. In fact, actually, let's do that right here. I'll do it right here. So flip the polarity. Okay, so now we have I in, negative terminal, positive, R. Okay, so when I check for negative feedback here, I get, again, the following, R. If this moves, but now the negative, and it comes back. So now, okay, I'm happy. And so I can now apply golden rule number 2 to this circuit over here. Right? And so, again, there's negative feedback. Check. So U plus equals U minus. Again, in this circuit, just so happened that U plus was equal to 0. Right? And then from these two, U minus will be equal to 0. Okay. And I'm just going to write one equation and solve this. Okay. And again, that will be U minus. So this is going to be V out. U minus V out over R. So that's the current is going there. Okay. What is the current that's going that way? Yeah. Right? And there is a current going that way, which is I negative. Okay. What is I negative? 0. Okay. What is U minus? 0. So this is golden rule number 1. This is golden rule number 2. Okay? And from this, I have that V out equals minus I in times R, or V out over I in equals minus R. Right. This is why we call it a transresistance amplifier. right? You put in the current, you get the voltage. So the ratio of the two is actually in units of resistance, right? So you would wonder, who wants this behavior? Right? But you actually already used it, kind of, in the lab. With this current signal, we can model the photodiode, for example, response to light. When you shine the light on a photodiode, you get current out. You get a tiny amount of current that you can then put into the op-amp in this type of configuration to give you the voltage at the output. And then you can use that voltage later to do interesting stuff. Right? So that way you can create like a light sensor. And in fact, we did that in a little bit different way in the lab, where you were trying to sense the pixels from that the projector was shooting in. Right? Okay, so let's do some more examples. Here is another one. And I'll let you do this one. Okay, here's a circuit. Again, I put an op-amp here as a triangle. I didn't put the polarity, because it's your task to look at this circuit and figure out what the polarity should be so that this circuit is in negative feedback. What this is, it's a voltage-controlled voltage source. Its value is controlled by VF, and VF is the voltage across this resistor R2. So it's our feedback voltage. But I add this sign, this negative sign here. So the value of this source is minus VF. Okay, yes? When we put the polarity, what was the question? Is it a different circuit? You mean different in terms of how it behaves? Yeah, now it's in negative feedback, right? There was a smiley face. Okay, so the question is solving this circuit the same as, I guess, this circuit, right? Well, the answer is no, because when we have a smiley face, negative feedback, then golden rule number 2 applies. And then U plus equals U minus. In this case over here, U plus is not equal to U minus. The op-amp cannot make it happen, right? And in here, the op-amp acts more like a comparator, so it will just slam one of the supplies to either VDD or ground, or VSS. Yeah, good question. Okay. Oh, sorry. Here it is. Okay. There you go. You have a minute. Okay, any takers? At least to get started. What should the sign be? Yes. Okay, so you're saying I would want this terminal to be positive, right? The lower one. Okay, so yes, that's correct. So let's see how to analyze it, just for people who are a little bit unclear about it. Okay, so we null the source. We have this piece. And we have the divider here. So let's label it, I'm going to label it first the opposite, right? Plus minus here. If I apply the change here, that change, well, let's say it will be a little bit smaller here. But then, because it translates with a negative sign through this voltage-controlled source, then it will actually be dropping here. And if it drops on a negative terminal, that means it increases on the output. Does that make sense? Anyone confused with this? Yes?
So what will happen if we have plus on the top and minus on the bottom?
So that's this case. Oh, what this is showing you that the circuit is really very aggressive, so to speak. Any little disturbance you put in will essentially cause the op-amp output to uncontrollably slam into one of the supplies. Because remember, this is showing you the output keeps increasing and increasing, right? But we mentioned last time it can only go so much to what the actual supplies of the op-amp are, right? So eventually it will hit one of the supplies. And if the initial disturbance was positive, it will hit the positive supply. If the loop reacts that way, if it's negative, it will hit the negative supply, right? But it will always stay at these two supplies. Right? That's not negative feedback, right? So for negative feedback, we want to do something like this, right? And then if you apply here the change, there's a change here. Again, there's a change here, but now it decreases the plus, right? So then the output will decrease. Okay. Yes? Oh, why did I get rid of this? Why did I not get rid of this? This is a voltage, this is a controlled source. It's not an independent source. It just maps some voltage within the circuit to another place, right? And so when we did equivalence, and so the question was, why didn't I get rid of this, right, of the controlled source? When we do equivalence, Thevenin, even superposition, you cannot turn off the dependent sources. They will just mirror something that's in the circuit. They are necessary. They are a necessary part of the circuit, right? So you cannot eliminate them. You will change the circuit behavior. You're not going to get what's needed. Okay, so now we have the negative feedback, so that's good. And now let's solve the circuit. Right. So solve it. Okay. I'm going to use that negative feedback polarity. R1, R2. Okay. So, who can tell me what is VF here as a function of V out? Yeah, it's a voltage divider, right? Great. So VF equals V out times R2 over R1 plus R2. Okay. Now, we know this circuit is in negative feedback. So, golden rule number 2 tells us that Vin equals minus Vf. Does that make sense? Everyone okay with this? V in is just V minus, or U minus, V minus Vf is U plus, right? So this is U minus, this is U plus, right? And this is one of these examples where none of these two, U minus or U plus, are ground, right? They're still equal because of the negative feedback. So keep that in mind. Okay? And look, I'm done, right? Because I just connect these two equations. I don't have to write anything else. So V in equals minus R2 over R1 plus R2 V out. And from there, I get that AV equals V out over V in equals minus 1 plus R1 over R2. So this is another inverting amplifier, right? Now, you may wonder, how the heck do I create this? That's not, well, it's kind of just a thing, but it's I didn't really show you how to build these in real life. Any ideas? How do I make this thing happen with an actual circuit? Yeah, inverting amplifier. We just learned that block as a function previously, right? So you just use that, and you can now create something like this, right? Okay, good. We're not going to do it here, but you can try and practice a little bit. Yes. Okay, yeah, sorry. Yeah. How I got the voltage divider? Oh, this one? Well, V out is here, right? V out is between this node, so let's call this U out, right? So U out is a potential. The output voltage is between that node and ground. So that same voltage is here, between U out and ground. So, and there's two resistors, so it's a voltage divider. Yes?
What is the ratio of V out to V in to AV?
We just call it that. Remember, A was this thing we used inside the op-amp, right? That was this really big thing, right? AV is kind of like a function, right? It's what I want the ratio to be. Right, and that could be -5, -100, something, right? That I want as a function. So we usually label it as, this is called voltage amplification. That's why V is there. Right? That's good. Yeah? Oh, how to make this? Well, the suggestion over there was, look, the function here from this input, if you treat Vf as input, to here is multiplied by -1, right? And we already learned what circuit can do that, right? It was basically, okay, let me find it where I had it. Yeah, it was this circuit, right? If in this circuit I make the two resistors the same, then the function is going to be -1, right? And so I can try to use that circuit just as an operator, as a block between this point and that point, right? Okay, good. So let's move on. I'm really excited about this part. Okay, so building energy efficient deep neural networks. you're laughing. IBM has invested, I don't know how much money in a new fab to build programmable resistors that will do exactly this type of circuit I'm going to show you for neural networks. And the reason is, I mentioned this at the beginning of the circuits module, module 2. And actually, at the beginning of the class, we told you about Moore's Law. Last 50 years, this is what basically made Silicon Valley and the whole industry. And we thought that's the greatest thing that we've achieved. Well, if you go and plot the rate of that improvement, which was doubling every 2 years, really impressive. And then you plot it, and OpenAI has done that. You plot the curve in last 6 years, what is the increase in computational demand for training of neural networks, from AlexNet today to AlphaGo 0. That is actually doubling every 3.5 months, okay? Which is basically a factor of 100 every 2 years. So now, on a log scale, there is a gap of 50x between what we've been able as a humankind to achieve in the last 50 years versus what we need to achieve given this new form of computation that we need to satisfy. And if you think you can do this 100x every year by just coding, well, you're gravely mistaken. If you think you can do it just with new technology, you're also gravely mistaken. So you have to make everything work. 10 layers of hierarchy, each layer by a factor, and you may be able to hit 10x every 2 years. Right? If you look at it over a course of 10 years, 10 to the 10th needs to be the improvement. So every layer of hierarchy has to improve by 10x. You have to be 10x better coder, 10x better circuit designer, 10x better technologist, 10x better machine learning expert at the top in the application level, etc., etc. So this is a very important thing. A lot of people are looking at how to compute with lower energy and faster. So I'm going to show you one way, and of course, 61C, you'll learn some other ways and things like that. So here is the basic thing. If you peel off these neural networks, you essentially get to one of the elements, which is a fully connected layer. And that's just a matrix vector multiply. Right? But it's a very important operation there. So we have our input activations, and you have your output results. And what you're doing is you're really just mapping. It's a weight. This is kind of the schematic they use. But it's just mapping. It's a weighted summation, right, of all the activations multiplied by the coefficients and summed for the output node. Right? And then by the same token, you come back here, and then you do AM1, AMN. Right? So I can write this as y equals AX. Right? And furthermore, we can expand that like we did in module 1. You can write that, x1 through xn, a11, am. So I'm going to show you now how to do essentially this slice. It's a vector-vector multiply where we take one row of matrix A and one column, and the X is an input. And then you can replicate these circuits in parallel so that they do each row separately. Right? Okay? So let's draw a circuit, and then we'll quickly analyze it. Okay? We're going to have our source. V in 1 will really represent x1, right? And then we have R1 dot 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 V in n. Rn R0 Okay? So, this is our circuit. Does it look familiar? Like if you, for example, forget these branches. Does this look familiar? Yeah. Or if you forget this, does it look familiar? Yeah. So, gut feel is like we can analyze this. We know how to solve this. Okay. So let's first check for the negative feedback. Right. When we want to check for negative feedback, first step is null all the independent sources. Right. So let's do that. We'll have plus here, a minus here. We null V in 1. It's R1. We null V in N. R0. Okay. So I'll move the output. What happens with this node? U minus. Does it go up or down? Why does it go up? There's a whole bunch of complex resistors there. How do we know it goes up? Yeah. Yeah, so when something looks daunting, try to simplify it, right? We use equivalence. So the suggestion was, hey, I noticed that all these, R1 through Rn, share the two nodes, right? On one hand, it's U minus. On the other hand, it's the reference node, ground. So they're all in parallel. And if they're all in parallel, I know I can represent them as an equivalent resistor. So all of this is now one equivalent resistor. So then it becomes a familiar thing. We did it at the beginning of the class, right? It's like an inverting amplifier, right? It's a voltage divider here between R0 and this R equivalent. Right, so this is like R equivalent. So in a voltage divider, I know that this voltage will increase. The same way that this one does, just for a factor lower. Okay, so if it increases on a negative terminal, what happens with the output? Yeah, decreases. Okay, great. I have negative feedback. So then let's solve. Again, because of the negative feedback, I know that U plus equals U minus. This is golden rule 2. What do I know about U plus? It's 0, right? So then U minus equals 0. Okay, so I'm going to solve it in one equation. Okay, so let's do that. We can focus on, again, this U minus node. And so just write the KCL there. So it will be U minus minus V in 1 over R1. So that's this current. Right, this is U minus. Plus dot dot dot. And then I have U minus minus V in N over Rn. That's this current. Right. Then I have U minus minus V out over R0. That's that current. And then I'll write plus I minus equals 0. And then let's just apply the golden rules. I minus is 0. That's golden rule number 1. From this over here, I know that U minus 1 is 0. Again, that's golden rule number 2. Okay, so I get that V out equals minus R0 over R1 V in 1 plus dot 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 plus minus R0 over Rn V in N. Does that make sense? So all of these are now my factors. Right? Those are the weights that I'm using here. So this will be, if this is now y1, this is x1, this is xn, then this will be a11, a11, a1n. Does that make sense? Questions? Yes? Great question. Is there a fast way to change the weights? Well, I just mentioned at the beginning something about IBM. There are actually materials, or called, let's say, phase change materials, that are where the resistivity of the material is a property of voltage that you apply across it. Right? So these resistors would have like kind of a wear out. I could push some voltages through these resistors, meaning make these sources in the training phase be something, so that I tune the value of this resistance to whatever I want. And then in the inference phase, I just put the signal through, and then the circuit computes what it's supposed to compute. Does that make sense? So you're basically using the same terminals to program the resistor with higher voltages. And then once you program them, then the circuit just spits out the answer once you feed the information in, right? So you have, in neural networks, you have the training phase and then the inference phase. And so in training phase, you would program these programmable resistors that way, right? That happens infrequently because most of the time you do inference. And the reason why low power is interesting, you won't have this on your phones, everywhere around you, small. And so you need this to be a low-power kind of inference engine. Right? Okay, great question. Okay, so that basically builds our artificial neuron. Right? Now, one thing here is, as you may notice, what types of weights can I have here? I'm a bit restricted. When you do the training, what comes out in terms of coefficients? They can be both positive and negative, right? I can here have only negative coefficients. So it's a little bit kind of weird, right? So I need to have a way to somehow invert things. So I could invert the activation, right? Or from stage to stage, I could invert the final function, and that way I'm kind of inverting the weight itself, right? So really what this means is that I'd like to have a way to compose these things together, right? So in this case, let's have something like this. So I want to essentially think in block diagrams. Right. So in our case here, what do we have? We had input voltages that were our activations. And, you know, these neural networks are actually pretty big. The fully connected layer in AlexNet is like 4,000 by 1,000. That's a huge matrix. That's a super humongous circuit. Try running that on a digital processor. It takes a while, right? It's 4 million elements. So let's say we do 1,000 inputs, right? And this is this fully connected layer, right? Or we can call it inverting summer. Actually, let me mark this here so that you guys know it. So this is inverting summer. One really nice thing about this that I forgot to mention is, unlike the summers that we did previously, where you have two voltages and resistors, in this one, each weight can be set separately. Notice that each weight has a separate degree of freedom, R1 through Rn. So remember that when you're building these signal processing blocks. It becomes a very handy block when you need to set the weights separately. Okay. So I have that block here, but I'm not happy with the polarity of what comes out, right? So, what I'm going to do? Well, I'll just apply the inversion block. Right? And then I get minus V out. Right? So, usually when we tell you to do something in some design task, this is exactly what you should do first. Read the problem and say, okay, what mathematical operations they want me to do here? Or what conversions from what physical variable to another? And then just sketch it out as a block diagram. One block, some function, another block. The more you break it down, the more you'll be able to map it to these blocks that we've learned in class. And then you don't have to do really any kind of significant brainstorming. Yes? So if I wanted to negate V out, wouldn't I make all the coefficients positive, right? That's true. I was just showing you, because if in neural networks, these layers are basically, how you could call it, the layers themselves are cascaded, right? So let's pick one output, U1. That U1 will become the activation into the next layer. And there, I can choose how I want to split it. If I'm driving it into the next coefficient path, I can locally invert it if necessary, right? And then it's the same as inverting that coefficient. Right? Okay. In the actual implementation, but I'm not telling you this, they make these phase change resistors be able to go both positive and negative. So you actually don't have to do all this. But yeah, that takes a little bit different physics. Okay, here you just really compose it as blocks. And then you can think, once you put the blocks together, now you've kind of divided and conquered the problem. Now you can look at each block and see, okay, how do I map it to what I know, right? So let's say here, so this is like concept, right? And always sketch the concept first, because you may be able to see that it's not really right how you're doing it, right there, without drawing extensive circuits. And then you go to implementation. Now, in implementation, some other gotchas may get you. And we're going to discuss them very shortly. Here, you're just wondering what is the sequence of mathematical operations and which belongs in which block. You don't care about currents and voltages and how they interact with each other. When we do the implementation, we start caring about that too. Right? But don't overburden yourself to think about everything at once. That's the key. So in implementation, I already know how to build this fully connected layer, right? We just did it, so I'm just going to draw it again. Right? Plus, minus, we have V in 1, V in N, R1, Rn, connect all of these, R0. Right, that's my first stage, right? And now I want to connect this to the next stage. This one is, okay, R, again, R, right? If this here I label as V out, right? I already know what this function is, and I'm just going to do this one as minus V out. Right? Now, I could do this in this case. I could add this circuit to this one without worrying that anything has changed in this one's operation. There's a single reason why I was able to do it. Does anybody see that? Why can this circuit produce the same voltage here with or without this inverting amplifier? Yes? Okay. So the answer was the inverting amplifier doesn't draw any current. Everyone agrees with that? In fact, let's check it out. What is this current here? If this voltage is V out, what is this current? What's the voltage at this node? 0. The voltage here is, or potential here is V out. So, unless V out is 0, there must be current through R. And that current is equal to V out over R. So it actually is drawing current. How come this circuit still keeps V out that's desired while providing current? What must this circuit be? Which element that we know can give you any current you want and still keeps the voltage? It's a source, voltage source, right? And indeed, if you look inside here, well, what's the model of the op-amp? A times U plus minus U minus, right? That's what's inside. So it is a voltage source. Because the op-amp's output is a voltage-controlled voltage source, this thing can provide any current to the follow-on circuit and will always produce the function. Does it make sense? Questions? Yes?
Wait, so why do you want the voltage source to give any current? Like, why is that necessary?
So, I have this function on the left, right? And I know that my V out should be a sum of these voltages, right? Well, when I attach this new circuit, I want that function to be the same. Here. Right? I don't want this circuit to change what this circuit is producing. And when I didn't have the inverting amplifier, this current was 0. Right? Current into here, because this just didn't exist. Now that it exists and tries to draw the current, the only way for this voltage not to change is that the voltage source provides the current. Right? And that's indeed the case. The op-amp itself, the output stage, is the voltage source. So this tells you it's safe to attach anything to an op-amp output. It will always produce, when you're cascading the blocks, if this block it has an op-amp and it's driving the next block, it's okay. You don't have to, it doesn't change the function. That's the key, right? Okay. So, in general, I'm going to show you a safe way to do this, meaning to map this directly to circuits without worrying. And once you do the safe way, you can then think of maybe simplifying the circuit, okay? So, block 1, there's an output. Here is block 2. Okay, this is some f function, this is some g function. What I'm going to put in between these two is an op-amp. Okay, but I don't want this op-amp to change these two voltages. This voltage is V1. This voltage here is V2. I want V1 to be equal to V2. Because I don't want this block to do anything except help me combine these blocks, right? So I'm going to write it up like this. So let's look at this block in the middle. What does it do? Is it in negative feedback? Yeah. If I move the output, it directly moves the negative terminal up, so it's in negative feedback. Okay, so it's in negative feedback. That means U plus equals U minus. What is U plus? U plus is V in. What is U minus? U minus is V out. Right? So actually, this block is really cool. It's called a unity gain buffer. It just passes the voltage with same value, but the current here is 0. So this element just takes this voltage, passes it to the output, provides an arbitrary current, while loading this previous circuit with zero current. So it's a perfect measurement of voltage. Perfectly measures the voltage and provides it to this other circuit. So regardless of what this circuit needs, that current is provided by this op-amp. Does that make sense? So whenever you have cascading, just insert this buffer in between the blocks and you'll be safe. Okay, we'll revisit this in the next lecture.
So I wonder, like for this case, how can I just like invert without changing it?
Hold on.